All right, so well, hello, class. I would like to go ahead and take a little bit of your time and go over what we left over for chapter 1.2. Okay, um, just to kind of catch up a little bit, we were discussing rounding, and we did one example, but we kind of ran out of time, and so I wanted to use this video to go ahead and complete the chapter and all the way through the modeling application, uh, and um, and then I'll see you guys next time so that we can continue with chapter 1.3. Okay, so why don't we go ahead and get started here? And here's the PowerPoint. And let me do this. I think this will be better. All right. Um, it says estimation by rounding, and here's an application problem. Oh, I do want to check something. I do want to check something. Pause sharing. Let me 1 second here. All right, I think I figured it out. So let's go ahead and get going. So it says that you purchase a bread for $2.59, detergent for $5.17, a sandwich for $3.65, and what a few more things, an apple and then a coffee. Okay, we can read how much each one of those was. The total bill was given as $24.67. Is this amount reasonable? Well, let's see. Why don't we go ahead and I will suggest for this example to round each one of these values. Ooh, let me see if I can make this better. Let's see if I can make this better. Otherwise, maybe the pencil tool will be better. Okay. Yeah, this is better. All right, so I will take each one of these values here and I will round them to the nearest dollar. Okay. For example, this $2. Oh, what's going on there? These, I don't know what's going on there. Let me stop for a second here. All right, so I didn't like what the computer was doing earlier, so I switched the mode. Any case, let's see if we can get it going now. All right, so what I said earlier was that we're going to take each one of these values, and I am recording, okay? And we are going to round them to the nearest dollar. So what I meant to say earlier was, for example, if we take these $2.59, we round it to the nearest dollar. Well, this is the nearest dollar here. So therefore we look over to the right and we see a 5 because it is 5, then therefore this becomes $3. And then we'll do the same thing for $5.17. We'll look at the 10th place. Since it is a 1, we're gonna keep this as $5. We keep the 5, and then these two become zeros. Then we got 365. We look at this place value is 5 or greater, so therefore this number becomes a 4. And then we have 0.47. Since this is a 4, then it is less than 5, we're going to keep this as 0. Okay. I think I probably could have done something better than that. I think what I'll do for that one right there, what I'll do for that one is I think I'll just make this 50 cents, and hopefully that make a little bit more sense because I just don't feel right with just making it 0. I mean, hopefully you know what I mean. Okay, 8.79. I'm gonna round this to, in this case, $9. And then we add this up, And then we get 0 here, we get 5. Let's see if I can add this in my head. 8 and 5 will equal to 8. 8 and 4 will be 12. 12 and 9 will be 2150. So it seems like our estimate is kind of low compared to the total bill. Okay, let me just double check the math here. 3 plus 5 is 8. 8 and 4 is 12. 12 and 9 is 21. Yeah, so I get 2150 as my estimate. So, I don't know. What we should do is, why don't we go ahead and take the actual numbers and add them up? Okay, so I'm going to use a calculator here because, well, even though I probably could do it in my head, I want to be a little bit faster. So hopefully you will pause the video and carry out this computation on your own. And the result that I get is 20.67. So I'm just going to look at this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We didn't miss any values. And so therefore, the bill appeared to be 2067. Something is off here. And therefore, this could probably be like, oh, what's going on? Why are you charging me $4 extra? Is there something? Is there something I'm missing in my bag? I would probably make an argument, as far as what could be the cost of this, or making some consumer questioning, so that otherwise I feel like I'm getting ripped off. Okay, that was this example. Let's move on. Let's try another one. And I think I might have to erase some of this stuff because yes, it is right on top of it. All right, so what I'm going to do is I'm going to erase some of this stuff. So hopefully, if you need to, pause the video and copy the information. I'm about to erase some stuff. All right, so let's erase some of this stuff. All right, I think that should do it. So let's go ahead and bring this out. It's a landscape architect. Works full time, earns $52 per hour. Estimate the landscape architect's weekly salary, and then also estimate the architect's annual salary. All right, so let's see if we could do this just by doing estimations. What we know is that people usually work about 40 hours per week. Okay, so to do an estimation here, what we could do is we could say, well, if we were to round the architect's what was it, the architect's salary per hour to $50, then we could do $50 times 40, which in this case will be 5 times 4 is 20, and then we add the 2 zeros. We can say that this is approximately $2,000 per week. It's about $2,000 per week. Using the same technique, we would like to estimate the landscape's architect annual salary. So, well, let's see, what can we do in this case? Well, we know that there is 52 weeks in a year. Well, what if we were to round this to 50 weeks? Again, we're doing an approximation. So we're gonna approximate that there is about 50 weeks in a year. Okay, so then now we know that this landscape architect makes about, oh, I can do better than that. I can do much better than that. We estimated earlier that the guy's salary is about $2,000 per week, and we're gonna multiply by 50 weeks. And so we roughly get, what is this? 5 times 2 is 10. And then we have 1, 2, 3, 4 additional zeros. 1, 2, 3, 4 additional zeros. So we can say that this architect makes about $100,000 per year. Again, I'm trying to use the rounding technique here and not necessarily trying to come up with exact values. Again, the whole purpose of this is to use a rounding technique. Please follow the instructions on the homework though to make sure that you're doing things correctly. All right, let's move on. Something a little bit more interesting. Okay, and I don't know how to get rid of this. Okay, there we go. All right, so we would like to talk about graphs, and the first one we would like to discuss will be circle graphs. And so let's just read what we have here. Circle graphs, also called pie charts, show how a whole quantity is divided into parts. Circle graphs are divided into pieces called sectors. Oh, that's great. So what we have here is an example of a circle graph or a pie chart, and it seems to be the home energy pie. We notice that it seems like based on this particular picture, 48% of the pie is dedicated to heating and cooling. For example, 11% is dedicated to the water heater, 7%. So I think we get the idea. Let's see what the question is or what the scenario in this particular example is. Suppose that last year your family spent 2,000. I'm about to get to a number here. I would like to go ahead and highlight it. I think I use this color. Last year, a particular family spent this amount on natural gas and electricity. Okay. Use the circle graph to answer the following questions. All right, let's see what the following questions are. Determine a calculation that shows the amount your family spent on heating and cooling for the year. Okay, I see that here. Heating and cooling is here. And it seems like 48% of the natural gas and electricity was spent on heating and cooling. But maybe I need to give a small lesson on cents and decimals. If we would like to write 48% as a decimal, then we can think of the number 48 and then imagine that there's a decimal point here. We move it 2 places to the left. And so, oh, what happened there? And so therefore we get 0.48. For example, 12%, its decimal representation is 0.12. 10%, its equivalent, its decimal equivalence is 0.10. And I'm just going to do one more example here. For example, lining, which is 7%, its decimal representation will be 0.07. I think I had enough for that. Let's move on to whatever we need to answer here. It says, determine a calculation that shows the amount of energy spent on heating, cooling for the year. Okay, so we had 2,148 with 72 cents, and 48% was spent on that. So what we do is we multiply that by 0.48. The answer will be equal to, and now I'm using a calculator here. So 2148.72 times 0.48. In my calculations, I get this. This is the number I got on my calculator. 1,031.38 and then 56. But because we are dealing with money, we only go to 2 decimal places. So therefore, we have to round this number. Therefore, since the number to the right of 8 is 5, this number becomes 39. So $1,031.39 is how much was spent on heating and cooling for this family. Let's look at the second question. Oh, use rounding to find a reasonable estimate for this calculation. Let me just do that again. I have this information here. Okay. I am going to erase some things so that way. Oh, what happened? Okay. I think I can still see it. It says use rounding to find a reasonable estimate for this calculation. So let me use some estimation here. I'm trying to write. Okay, here we go. I'm going to round this number to $1,000. I want to make my life a little easy. Okay. And this 48% we see here, and I guess I could write it here. And this 48%, I'm going to round it to 50%. So therefore, I'm multiplying by 0.50. And so therefore, this is actually an easy calculation. I'm taking just half of 2,000, which is equal to 1,000. And notice that doing that is very close to the actual amount that we got earlier. Okay, based on our estimate, our value is actually not too far from the true value, which is of course 1031.39. I think in a way, if we wanted to do some computation on the go, we were at the store or something like that, we could say, well, this is going to be roughly about $1,000, whatnot and what so. Okay. All right, let's move on and continue with, I think we got two more examples. Let's go ahead and get them done. It says formula is a statement of equality that uses letters to express a relationship between two or more variables. The process of finding formulas to describe real-world phenomena is called mathematical modeling. Such formulas, together with the meaning assigned to the variables, are called mathematical models. Okay, so for the next two examples, we're going to need the following formulas, okay? We're gonna need the formula for a line, okay? That formula looks something like this. Y equals mx plus b, okay? We will probably talk about this a little bit more. I'm not sure when, or maybe no, but I think so. I think so, but I don't remember right now. In any case, m is the slope. In other words, the steepness of a line. And there is another formula for slope. That is y2 minus y1 over x2 minus x1. Okay. This b right here is referred to as the y-intercept. And so a y-intercept is where a graph crosses the y-axis. Okay. So I'm just going to put here y-axis, but I'm not really sure why I'm really writing this. Okay. But in any case, I know or I remember, I shouldn't say I know, I remember from the last time I took this class that in order to do the next example, we need these formulas, okay? The equation of a line, and of course, the slope formula as well. All right, so let's go ahead and check out the next example. We need to pause and write this down, and so that we can go ahead and move on to the next example. Bar graphs. Bar graphs are convenient for comparing some measurable attribute of various items. Here, what we're looking for is there will be something called a histogram later on. And how do we, so let me just, since I said it, I want to just write it down. I also said the word histogram. But these two are very similar. A histogram will look something like this. But notice that it also uses rectangles. What is the difference? Well, the difference is that a bar graph, there will be some clear gap between one rectangle and the other. Do you notice that here? There is a gap between this set of bars to this set of bars. In a histogram, we don't find that. In a histogram, we find that these rectangles actually share a common side. Okay, so there will be no gap between them. All right, so let's go ahead and just get through the example and see what kind of jelly jam we get ourselves into. It says, use the bar graph to estimate a man's increased life expectancy rounded to the nearest hundredth per year for each subsequent birth year. Okay, that's great. Let's see. It seems that we want to estimate a month. So in this case, we're going to have to look at only males. Increased life expectancy. So what we notice is that the life expectancy of a man has increased over time. And it seems like the very first one, according to this data, of course, in the 1950, it was 65.6. And in 2020, a man's life expectancy is 77.1 years. Okay. Rounded to the nearest hundredth of a year. Okay. So we need to come up with an equation here. Okay. And so okay, so in this case, we need the slope. Okay. We need the slope formula. I should just say it like that. We need the slope formula. And so in order to do that, okay, what we want to do is try to explain this a little further. We want to know at what rate is man's expectancy increasing from here all the way to there. So it is increasing at some rate, and that's what we're trying to find out, okay? At what rate is it increasing? And so in order to do that, we use the slope formula, okay? Which is, helps us find rate. So in this case, okay, okay, is I'm going to use this point and that point right there. Okay. And so the way I see that is in this way. Okay. We have 2 points. The point 1950, comma 65.6. And I see another point which is 2020, comma 77.1. Okay. So this will be our x1, y1, x2, y2. So to find this rate, I'm just going to write here rate, which is also slope. Okay. I'm going to use this formula, which says y2 minus y1 over x2 minus x1. But what I'm going to do is I'm actually going to use estimation because maybe I would like to try to do this by hand and without the use of a calculator. Let's see. I am going to round this to the number 80, and I'm going to round this number to the number 70. that it makes for easy computation. Okay, so we have 80 minus 70 divided by, in this case, 2020 minus 1950. 80 minus 70 is 10. 2020 minus 1950, that will be 70. And we have 1 over 7. Now we could probably say, let me just, 1 divided by 7 is, I get here, using my calculator, 0.1428. I just want to write as many decimals, 57. And so let's see. We want to know this number rounded to the nearest 100th of a year. 100th. That is 2 decimal places, so therefore 0.14. All right, so in conclusion, it seems like the life expectancy of a man is increasing at about 0.14 per year. Again, let me say this in conclusion. Based on my computations and on what I did here, it seems like a man's life expectancy is increasing by 0.14 per year. Okay, that based on my computations here. Okay. All right. I think I'm going to leave this example alone. One thing that I could probably do different, since I do have a calculator, is probably this. Okay, so I'm going to do this. I guess not that I would like to redo the example, but since I don't remember exactly what my MATLAB wants, but one thing that we could do is one thing that we could do is we could actually put those values, the exact values here. All right, so let me do that. Let me do that instead. And then I'll round to the very, very end. Okay, so let me do that and see what happens. See how much different we were. So here we had 77.1 minus 65.6. Okay, so I'm going to do that in my calculator. I don't know how to use my calculator. Apparently. Minus 65.6, 11.5. And then I'm going to do, whoa, okay, this number doesn't make sense. And then I'm going to find out what that is in my calculator. And I get 0.1648. I'm just going to put 28. And then once again, if I want to round it to the nearest 100th, that is here, so we get 0.16. So based on these on the exact computations, the life expectancy of a man is increasing by 0.16 per year. Okay, I am leaving this example alone. I am moving on to the next example. Okay, so I guess I will say this. One more comment on this particular example. It's not my favorite. I think we can definitely find easier examples than this one, but I think it's in your homework assignment, so I tend to complete this example, even though it might be a little bit too much for some of us to even understand. Okay, and so hopefully I did a good job of trying to explain the fact that there is a formula. If you know what the formula is, then we can just apply the formula. And then here at the very end, it seems like I'm actually using the rounding technique that we talked about it within this chapter. Okay. All right, so I'm going to do another example here. It says line graphs. Okay, so we see another type of graph. Line graphs are used to illustrate trends over time. Some measure of time, such as months of years. Okay. So what we notice is that the x-axis is, we notice that with this particular graph, we have a continuous graph, so there is no gaps, and this is usually over some period of time. And you're probably wondering, well, how is that different from the previous example? The previous example also had time, but the thing is, we're not, in this particular case, we will use a bar graph because we want to say in 1950, we had this value. And then some computations were done in the 1960s, and then we got this value. So it is not a continuous computation, it was a more discrete situation. We do it at this time, we did it at this time, we found a computation at this time, we found a computation at this time, versus in this example, is continuous computation. So we get a continuous graph. In any case, let's just go ahead and move on. Okay. It seems like we're looking at percent of college students, cigarette use by US college students, and this is the percentage, and from the year 1982 to the year 2014. I'm noticing that there is a decrease from 1982 to 1990, but then there was an increase in cigarette use from the 1990 to 1998. And then since 1998, I believe this is when cigarettes began to disclose the fact that they cause cancer, and so we could see that since then there has been a decrease in cigarette use by U.S. college students. But again, I could be making this up, but we obviously see that there is definitely a decrease after 1998. But let's look at the questions. What kind of questions we run into here? It says, find an estimate for the percentage of college students who smoke cigarettes in 2010. Okay, this is actually pretty decent. 2010, it seems like, I think this is 2010. All right, from here to here is 8, so therefore, yep, that would be 2010. Okay, so, okay, so in 2010, notice my technique where I say, okay, let me go meet the graph. Okay, so it's here. And then, so where is that on my y-axis? Oh, I'm trying to do as a straight line as possible. I would like to say that this is roughly 18%. All right, my best guess at this, using my technique here, will be that 18% of the students use cigarettes. If you believe that's 17%, I don't know if I could disagree with that. If you say that's 19%, I think it would be difficult for me to disagree with you. However, if you say 16 or 20%, I will have to disagree with your answer, okay? All right, let's move on over here. It says, in which 4-year period, did the percent of college students who smoke cigarettes decrease at the greatest rate? So we're looking for something really steep in this direction. In which 4-year period? So in which one of these intervals from here to here, or from here to here, or from here to here, 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 from here to here? In which one of those 4-year periods did we see the biggest decrease in cigarette use by US college students? And I think by looking at this, it's right here. Okay. I'm looking at a really, really steep line over there, or line segment from this point to that point. Okay. We could definitely say that it's definitely not this period and not this period, because during those 4-year periods, the lines are increasing. Okay. But again, with these type of questions, when you're looking at where you're being asked to determine the in which period you had the biggest decrease, or it could also be increase. You want to make the connection that you're looking for something really, really steep. And in this case, we can see that the percentage from here to here is a bigger decrease than any other 4-year period. Okay. All right, let's move on. So we're going to say that that was from, what is it, 2002, from 2002 to 2006. Okay. Is there another question? Yes, there is. I didn't even touch the computer. It just came up by itself. All right. In which year did 30% of the college students smoke cigarettes? 30%. I'm going to say that that's 30% right there. And let's see, 30%, I'm going to say is this point right here, which is this year right here. And so therefore, I will say that was the year 1998. All right, so hopefully you saw my technique, especially for question A and question C, where, if I'm trying to answer questions about the graph or data that is on the graph. And I think that was no more questions there. Oh, no, more mathematical model. Okay, this has to be my last question, and then I'm done for the night. Okay. So the bar graph shows so here it seems like we're about to do some mathematical model. We used formulas before. Now we see if we can put a couple of more things together for this example. So let's see. Okay, I'm trying to change my ink. Here we go. The bar graph shows the average cost of tuition and fees for private 4-year colleges. Okay. Well, but just by looking at the picture, we have a bar graph. We also notice that there's an increase in tuition. All right, and it seems like the data began from 2000, or this data goes from 2000 all the way to 2016. That's 16 years. Okay, 16 years worth of data. Okay. All right, estimate the yearly increase in tuition and round it to the nearest dollar. Okay, so to do that, let's see if we can piggy bank on that slope. I don't even know what I wrote there, but slope, also the rate of change. And that formula was y2 minus y1 over x2 x1. So let's see, maybe I could do that computation up here. I'm going to change some numbers. So let me go and change some numbers. Okay, I'm going to do that computation up here because I know that I'm noticing that there's another question there. So I'm going to say 33,480 minus, you know what? I don't even know. I'm not even using my rounding techniques. What's wrong with me? What's wrong with me? I'm not using my rounding techniques. Okay, let's use the rounding techniques. We learned them. Might as well just go ahead and use them. Okay, so I'm gonna say 33,000 minus 15,000, or maybe I could say 16,000, right? Maybe I should say 16,000. So that's not good. That wasn't a good rounding technique. Okay, here we go. 16,000. Here we have 2016 minus 2000. And let me try to explain why I did that. Okay. This would have been the point 2,000, 15, 5, 18. So this is the x1, y1 value. And this number up here would have been the point 2016, 33, 480. So that is x2, y2. So if you see the formula, it is this number minus that number, and then x2 minus x1. Okay, hopefully that makes sense. Going back to our computation here, this will be 17,000 over 16. Ooh, okay, almost. I almost. Okay, but I guess I use my calculator now. Divided by 16, and this is roughly, I want to say 1,062.50. All right, so at the end, yes, I did use a calculator. I understand that, okay? So approximately, tuition has been increasing. So what does this number mean? So there has been an increase in tuition by a little bit over $1,000 per year. All right, that's what this number means. There has been an increase in tuition of a little bit more than 1,000 every year. Okay. All right. So moving on to part B. Write a mathematical model that estimates the average cost of tuition after year 2000. Okay. So here's where the whole y equals mx plus b is coming from. Okay. So the model that we're going to write would look like this. T is equal to 1,000. I'm gonna even say, what was it? The nearest. I actually didn't answer the question. 1,063. Okay, to the nearest dollar. So 1,063. Okay, times x, which will be the year, plus 15, or I guess since I'm rounding, I'll use 16,000. Okay. All right. And so this will be a mathematical equation that could help us estimate value of tuition. Okay, the tuition for a 4-year college after the year 2000. Okay, so roughly something like this. So look at how we can use this. It says use what you wrote in part B, which is this equation here. Use what you wrote in part B to project the cost of tuition the 4-year college in the year 2020. Okay, in the year 2020. This is 20 years after 2000. So to use the equation, tuition will be equal to 1,063 times 2,000 plus 16,000. This is using my estimations. So 1,063 times, oh, what am I saying? What did I say? 2,000. I meant to say 20. I meant to say 20 here. Okay. Times 20. That will be 21,260 plus 16,000, which is at the very end, plus 16,000. Let's not make a silly mistake. That will be 37,260. So based on my estimations, I predict that in the year 2020, tuition for a private 4-year college will be somewhere around 37,000. Okay, will be somewhere around 37,000. Alrighty then, I think that does it for chapter 1.2. Yes, it does. I hope that it was useful. And I know that towards the end, it got a little bit more complicated than we probably saw at the beginning of our class. Um, but I think we just got to get through the homework and hopefully follow the same models that I've done here. And but just let me know if you have any questions, okay? Thank you guys, and I'm about to close this out. Let's see. Wait, I don't know. I don't think I'm doing things right. So, okay. Bye bye.